Okay, guys, today we are going to talk about vectors in 3D, what is called Cartesian vectors. Or maybe I should call it forces in 3D. Everything we're going to be applied to forces. The first concept that we have to introduce here for handling vectors or forces in 3D is the unit vectors in the direction of the axis. I must say that in 3D, what's most important is to be very organized. 3D operations can get very messy, so you have to be very organized, and most important that you have to do very nice drawings in order to be able to see the angles very clearly. Angles can get very confusing in 3D because of the perspective. So in order to be clear about the components and the equation, it's really important to make good, nice drawings. So let's take a look at this. We see here a vector A in 3D. And what we are going to do here is that we are going to work everything based on rectangular coordinates. This is vector A. Vector A has three rectangular components. The rectangular components that we are going to working in 3D is obviously the components that go in the direction of the axis XYZ. So the idea is to get the composition of the vectors in the rectangular components according to these three axes, x, y, z. And in order to work very organizedly in the 3D, the concept of unit vectors is very important. So we already talked about vector I in the direction of x, vector j in the direction of y, vector k in the direction of z. This here on the drawing is in bold characters, but if you are writing by hand, it would be better to denote these vectors as I, J, and K with a little hat like that. Those vectors, all of them has magnitude of 1. Magnitude of 1. So they just have direction. They indicate the direction of a vector. I, J, K are vectors of unit 1 in the direction of of x, y, and z. So this vector A, and the concept of components is the same that we did for the 2D. Components of a vector are those vectors that when you add them together, you get as a result the original vector. So here you want to write this in like better like handwriting. This is vector A is equal to vector x or component x plus vector y, ay component y plus ac or component c. That's a better notation when you are doing handwriting. Or we can do this for a force. Will be something like this. This a force could be expressed as a summation of its components, the component of the force in the direction of the x-axis, the component of the force in the direction of the y-axis, and the component of the force in the direction of the z-axis. Now, if we express each one of the components as a function of the unit vectors I, j, and k, we have this expression here. Let me put it in handwritten. Vector A will be equal to the magnitude of the component x, will be just ax without the hat, multiplied by the direction, which is the vector I, plus a sub y, which is the magnitude of the component in the y direction without the hat. That's the magnitude. The direction is given by the unit vector y, plus the magnitude of the component in the z direction, which is a sub c without the hat because just the magnitude multiplied by the direction, that will be k with the hat. So this is magnitude, this is magnitude, this is magnitude, this is direction, this is direction, and this is direction. So we are going to be talking about this way of representing vectors. It's going to be very common. when we are dealing with vectors in 3D. Let's take a look at another equation that's going to be very important here. This equation is also very useful here, the one here on the rectangle here, that the magnitude of a vector can be found by Pythagorean theorem as the square root of the sum of the squares of the components. And this is very easy to demonstrate here. If we do a blowout of this lower part here, we have the x component and the y component of vector A. This is vector A. And by Pythagorean theorem here on this gray rectangle here, the A prime, this diagonal here, square is equal to this square plus this square. Very simple equation that you guys all know, Pythagorean theorem on this 2D triangle, 2D right triangle here at the bottom of the XYZ space. Now, if we look at the, let me write this here. If we look at the whole picture here in 3D, now looking at this blue triangle, this blue triangle is a right triangle also. It has a right angle here. So you have, by Pythagorean theorem, you have A prime square plus this distance, which is z, is the z component, right? That magnitude is equal to this height here from the whole height of the figure right there. So you can get also the Pythagorean theorem for that triangle, where this square is equal to this square plus this square. So this is A prime square plus the total height AC square. So now we can get A prime here from this expression here and put it down here. So we have this expression here, is this one right here. So we have A square, which is the magnitude of the whole of the original vector, as the summation of the squares of the components. Very simple equation. And that's if you get the components of a vector, you can get the magnitude by Pythagorean theorem in 3D. Very important equation right there. Another important concept when working in 3D is what is called coordinate direction angles. You just have to know that we call the angle that the vector makes with each one of the three axes x, y, z. Those angles are called alpha, beta, and gamma. Alpha is the angle that the vector makes with respect to the x-axis. Beta is the angle with respect to the y-axis, and gamma is the angle with respect to the z-axis. So that's when things begin to get a little complicated to visualize in a 2D plane, which is your paper or your screen, from a 3D vector that is in space. So look here, the angle alpha goes from the vector to the x-axis, the beta angle from the vector to the y-axis, and the gamma from the vector to the z-axis. Alpha, beta, and gamma. Angles with respect to the coordinate axis x, y, and z. All right. If those angles are with respect to each one of the axes, we can visualize here three right triangles. Maybe the easiest one to see here is the one with respect to the y-axis. Let's look at that. If we look at the vector A and the y component a sub y here, if you see this parallelogram here, then you look at this diagonal of one of the sides of the parallelogram, you have this right triangle. This like pink triangle here. Let's take a look at that triangle here. Is the pink triangle. In the pink triangle, you can see that the cosine of beta is equal to the adjacent side divided by the hypotenuse. This one right here. That's the cosine of beta. So the cosine of the angle that the vector makes with respect to one of the axes is equal to the magnitude of that the component with the component in the direction of that axis divided by the magnitude of the total vector or the original vector. We can see the same for the other two axes, but it's a little more difficult to see on 3D, but let's try. Let's say the x-axis here, you see the blue triangle. With the blue triangle, this diagonal here, with this will be the what we call it, the adjacent side. This will be the adjacent side, right, of the angle, adjacent side, and this will be the opposite side. Remember the sine, cosine, tangent, and this will be the no, no. Let me redo that. I need to erase here. Let's look at the blue triangle. It's a little difficult to see. If I maybe try to draw it here on the side, this line is one of the lines that make up the right angle here. The right angle is here. So the AX will be one of the one of the sides of the triangle that produce the right angle. This line here will be this line here that makes the right angle, and the blue vector will be here. That will be the blue vector A. This at the bottom on the floor, this will be this AX, and this angle will be alpha. This is, even though it doesn't look very much like, this is the blue triangle on the 3D picture there. And the cosine of alpha will be AX over A. So that's this expression here. Cosine of alpha is AX over A. Same thing with the other kind of gray triangle here, this triangle here. If you look at the blue triangle, the gray triangle here, you have the right angle here. I hope you can see that this is a right angle, because look, is the angle that makes this line that is on this top side of the rectangle, and is the angle that makes with one of the sides or the edges here of the parallelogram. So this angle has to be 90 degrees. 90 degrees. If this is the angle gamma here, the cosine of gamma will be this AZ component divided by A, which is the original vector, which is the hypotenuse of this right triangle right here. So that's this expression here. All right. Those three cosines, the cosine of those three angles, are called the direction cosines of the vector A. The direction cosines of a vector are the cosines of the angles that this vector makes with respect of each one of the axes. And those cosines are equal to the the component with respect to that axis divided by the total magnitude of the vector. That's a very, very important concept, and we will be using it all the time in order to find either the components of a vector or to find the vector when you know the components. Important concept right there. Another concept that is important to deal here is the concept of a unit vector in the direction of any given line or any given vector. Let's say we're talking about here the unit vector on the direction of the vector A. If you had a vector A, which is represented here by its rectangular components, and I would like better to keep the handwriting notation, equals to ax times the vector I plus ay j plus az k. The magnitude of this vector A, as we saw a couple of slides before, is the square root of the components square. So this vector has a magnitude A without the hat. So if I divide a vector which has a magnitude of A, I divide it by A, which is the same magnitude, the total magnitude of that division will be 1. So here I am taking a vector A, and I'm dividing the vector by the magnitude of the vector. So remember at the very beginning of the class that we multiply vectors by scalars, and then we have a new vector with a different magnitude. The magnitude of the new vector will be the magnitude of the original vector multiplied by the scalar that we are using to the multiplication. It's just basically one scalar by another scalar. Well, in this case, we are doing division. It's basically multiplied by 1 over a scalar. So here I have a vector. A vector has magnitude and direction. The magnitude is A. The direction is whatever direction has the vector A. And in the denominator, we have a scalar, which is the magnitude of A. So the number at the top will be the same number as at the bottom. So the total operation here is going to give us a magnitude of 1, but I'm going to put vector because it's a 1 that is going in the same direction as vector A. Actually, that vector is called u sub A. This vector is called u sub A, this one right here. This vector u sub A is a vector of a magnitude of 1 and in the same direction of A. If we use this notation here of vector A and apply it here, so we'll have ax over a I plus ay over a j plus az over ak. We saw in the previous page that ay over a is the cosine of alpha. We saw that ay over a is the cosine of beta, and ac over a is the cosine of gamma. So this is another way to express the unit vector in the direction of A. Can be expressed as cosine alpha I plus cosine beta j plus cosine gamma k. And this vector has a magnitude of 1. And using the Pythagorean theorem in 3D, we know that the magnitude of this vector, which is 1, is equal to the square of, actually here, to be strict, this should have a square here, right? This should have a square here, but 1 square is equal to 1, so it's okay. So the magnitude of the vector is equal to the square of the components. I said that this is equal to 1 square, but 1 square is equal to 1, so it doesn't matter. So we have this equation, which is very important to remember. The squares of the direction cosines, the squares of the direction cosines is equal to 1. Very important equation. Actually, I failed to write it down. I don't know if it's written in the next page. Cosine square of gamma is equal to 1. Is equal to 1. Very important equation here. So remember what is everything here. Alpha, beta, and gamma are the angles that vector A makes with respect to x, y, and z. If you take those cosines of those angles and get the square of those cosines and you add them together, you get 1. This is a very important equation that's going to be very useful. And now you can express the vector A. Vector A can be expressed as the magnitude times the direction. I love this notation. A vector is equal to the magnitude times the direction. In the hand notation, I would like to write that as a vector equals to the magnitude of the vector times the direction of the vector. Also a. I'm gonna put it the little hat like this because that's usually the case when you are dealing with a unit vector. You put that little hat. So this is a vector is equal to this expression that has here the magnitude of the vector and here the direction of the vector. And then you are expressing here in terms of the rectangular components. A cosine alpha is the x component multiplied by the unit vector in direction of x. A cosine beta is the magnitude of the y component multiplied by the unit vector in the y direction. A cosine gamma, which is the az component multiplied by the direction in the z direction. All right. What next? This is just a way to obtain components of a vector when you don't have exactly the Cartesian the coordinate angles, but you might have some other angles, and that is not always the case that you have exactly the xy components or the alpha beta gamma angles. Sometimes you have other angles. So this is kind of like an example of a situation that you might encounter. You might have a vector here, a or a force, and you know the angle with respect to the z-axis, and you have the angle that the projection of that vector over the floor or the xy plane um, produces with respect to the x-axis. That's a case that you might encounter eventually. So how do you deal with that? Well, it's just a matter of use your intuition, your ingenuity to figure it out. Then what you will do in a case like this is that if you have this here, say you have this angle here theta, right? And you have this no, stop. Aquí lo que tenemos acá. Now let's say that you don't have the coordinate angles, but you have these angles here, phi and theta, where phi is the angle with respect to the z-axis, and theta is the angle of the Okay, let's see another case that you don't necessarily have the coordinate angles, but you may have this situation here where you have this angle theta and this angle phi, where phi is the angle with respect to the z-axis, and theta is the angle that the projection of your vector on the xy plane makes with respect to the x-axis. Okay, so how would you get the components and the direction cosines of your vector? Well, this A prime, which is the projection of your vector in the xy plane, you can find it based on the magnitude of the vector by the cosine of phi, right? With this expression here, that will be A prime, will be A sine of phi, phi being this angle here. And once you have this projection here at the bottom, you can get the components x and y based on the theta axis, right? On the theta angle, sorry. So where ax will be a prime cosine theta here by looking at this right triangle where this is the 90-degree angle. It's getting a little messy, so you have to be very clean in this. Sorry, I'm not being very clean here. This is the 90-degree angle here. So A prime was A sine phi, so the x component will be A sine phi cosine phi. And same thing with the y component. The y component could be found by taking the A prime projection, A prime projection multiplied by sine of theta, right? Sine of theta. And A prime comes from here, so the y component will be A prime sine phi sine theta. So you can find now your vector A as the three components. This will be AX, this will be AY, and this will be AC. This is a formula that you don't have to memorize, not to memorize. It's just a matter of knowing your trigonometry, make good use of your sines and your cosines, and this is just basically like a particular case that you might encounter eventually. You not necessarily have the three alpha, beta, and gamma angles. You might have some different angles or different coordinates, and you have to deal with whatever you have in order to find what you need. Don't memorize this. You just have to make a very nice drawing. Make sure the angles show as clearly as possible. In 3 is not necessarily very easy, and the perspective that you draw sometimes is not good to provide a good view of the angles. But the idea is to find a way to look what is the sine, what is the cosine, so you find the right projection and the right component. All right. Now, all these equations that we have seen here so far, not many. Actually, we have seen very simple stuff. Basically, that the cosine, each one of the components is just given by the magnitude of the vector multiplied by the direction cosine. The magnitude is by Pythagorean, the square root of the components square. That's basically all we have done here. And the unit vector in the direction of a force is made of the direction cosines multiplied by each one of the unit vectors in the direction of the angle of the axis. Now from here we can jump directly to how to do summation of forces. If you have a couple of vectors, we can say a couple of forces, A and B, I would like to put here, this looks like it better like this, with the little hats here. So these are the Cartesian way of writing those vectors. I have vectors A and B or forces A and B, and I want to find the summation of those forces. So I want to find R, which is A plus B. Sorry. So in order to find the resultant of a couple of forces, or could be many forces, if you find a way to get the composition of those forces in the components x, y, and z, in this case ax, ay, xz, and bx, by, and bz, in order to find the resultant here, you just write the vectors in the Cartesian way, and then you make the summation by directions. If you do this summation here, x, ax plus bx, this will be the component in the I direction. So this will be what we have down here. This summation here will be this one right here, and this summation here will be this one right here. So that will be the x component of the resultant. This will be the y component of the resultant, and this will be the z component of the resultant. So the resultant will be equal to rxi plus rxy plus, sorry, I know somebody catch this, ryj plus rck, where if this were a force, this will look better like this. The resultant force equals to the summation of all the forces. I will put here, no, this doesn't look nice. Let me get rid of that. The summation of all the vectors or the forces that you are dealing with here. So, and that summation, if you write it as components here, then you will have the summation of the components in the x direction, summation of the components in the y direction, summation of the components in the z direction. And summation of the components in the z direction right here. And that will be how you find the resultant. Now, if you want the magnitude of the resultant, let me write this here in 1 second so we make a little room for the magnitude of the resultant. The magnitude of the resultant, actually, let me make a little room here. Make a little room here. Oh, we do some room here. Hold on 1 second. Make some room here. So you have the resultant equals to rxi plus ryj plus rzk, where rx is this summation here, where ry is this summation here, where iz is this summation here. If you want the magnitude the magnitude, sorry, if you want the magnitude of the resultant, well, you apply the Pythagorean theorem, Rx square plus Ry square plus Rz square. And if you want the angles that this resultant makes with respect to the axis, which are the direction angles, hold on one second. If you want the direction angles, then you can get them using the direction cosines. Alpha will be the arc cosine of Rx over R. Beta will be the arc cosine of Ry over R, and gamma will be the arc cosine of Rz over R. All right. And that will be it. That will be the way to deal with summation of forces in 3D. Basically, reviewing everything, you have your forces. You should have some information about the geometry, some dimensions, some angles. So based on what information you have to find the rectangular components of the forces. Once you have the rectangular components of the forces, you just have to add all the x components, all the y components, all the z components. Once you have the resultant x, resultant y, resultant z, that's basically your resultant. So you can write it as a Cartesian in a Cartesian way. R equals to Rxi plus Ryj plus Rzk. If you want the actual magnitude of the force, will be using the Pythagorean theorem, square root of the components square. And if you need the direction of this resultant with respect to each one of the axes, you can get the cosines by dividing each one of the components divided by the total magnitude R that you just found. So those are the cosines. If you get the inverse cosine of those, then you get the angles. That's it. Now we just have to make some examples.